We're going to take a look at solving systems of equations. There are several different systems of equations. They can have linear equations in them, quadratic equations in them. Here we're going to look at linear systems involving two variables, but later we'll look at systems involving three variables. But there are different methods for solving these systems of equations. Today we're going to talk about the substitution method for solving linear equations. So a system of equations is a set of equations that involve the same variables. A system of linear equations has each equation that is linear, like y equals mx plus b type of equation. A solution of a system is an assignment of values for the variables that makes each equation in the system true. So to solve the system means to find all the solutions that make both of these equations true equalities. So here's an example of a system of linear equations in two variables. First we have 2x minus y equals 5, then we have x plus 4y equals 7. These are equations of lines, and so if there is a solution to this set of equations, it's going to be the point of intersection of the graph of these two lines. So I wouldn't expect more than one solution to these, but there are other variables that come into play. There could be more than one solution, and we'll talk about that. There may not be any solution at all. So let's use the substitution method to solve these linear equations. And here's what we do. Here is the step-by-step process. We're going to choose one of the equations and solve for one variable in terms of the other. So we're going to have y equals, or we're going to have x equals with everything else on the other side of the equal sign. Then we're going to substitute the expression that we found from the first equation in step 1 into the other equation for that variable. So now we'll have one equation in one variable only, and we can solve for that variable. And then we will back substitute into one of the equations to solve for the other variable. So it sounds complicated, but it's really straightforward. So let's use 2x plus y equals 1 and 3x plus 4y equals 14. I'm going to take equation 1 and I'm going to solve it for y. I'm going to put y completely in terms of x. So you can see all I had to do is just subtract 2x from both sides. So now I have y equals 1 minus 2x. And remember, I've spent a lot of time talking about the power of this little symbol right here. Equals means equals. If y equals 1 minus 2x, then everywhere I see y, I can write 1 minus 2x instead. That's the substitution method at its heart. So I take that second equation, and where it has y, I substitute 1 minus 2x, and just as I said, now I have an equation in only one variable, in the variable x. I use good algebra, gather like terms, solve for x, and I find that x equals negative 2. Now I have a value for x. I need to back substitute into one of those equations and find a value for y. So I'm going to use y equals 1 minus 2x, substitute the value of x equal negative 2, and I find that y equals 5. So x equals negative 2 and y equals 5 is the solution. It's the ordered pair negative 2, 5, and you can see graphically that is the intersection point between the graphs of those two lines in the plane. So when we're solving linear systems, we would expect to get the coordinates of a point in the plane where they intersect. So the number of solutions of a linear system in two variables can be something other than exactly one solution. Just as we saw a while ago, if I do get the coordinates of a point, then that is the point of intersection of those two lines in the plane. But there is the case where I may be dealing with two parallel lines and I don't get a solution at all. So if I don't get a solution for x or for y, then it would make sense that I'm dealing with parallel lines and that those two equations never meet. They never have that point in common, so there would never be a solution to that system of equations. The technical word for that is that you have an inconsistent system. The third possibility is that we're dealing with a different form of the equation of the same line. The system has infinitely many solutions. I may have two equations, but both of those equations may be the equation for the same line in the plane. So those two lines are lying right on top of each other, and they intersect everywhere from negative infinity to positive infinity. That's why we say it has infinitely many solutions. And in that case, the big technical term for that is that we have a dependent system. So remember, we may not always just get the coordinates of a point. When we're working on homework tomorrow, we could get no solution or we could get infinitely many solutions. So let's work one more example using the substitution method. Here we have 3x minus y equals 0 and 5x plus 2y equals 22. I'm going to take the simplest of these equations. If I take this one, I'm probably going to have fractions involved. Nothing wrong with that, but if I can make it simple and quick, I'm going to make it simple and quick. So I choose equation 1 because it's the more simple of the two, and I solve for y. Here, if I add y to both sides, I have y equals 3x. I take the second equation, and where there is y, I substitute in what y equals, and y equals 3x. Gather like terms, and I find that x has a value of 2. Now I'm going to back substitute into, and I can back substitute into either one of these equations. It doesn't matter which one that I use. So I'm going to back substitute here into this equation, and I find that y equals 6. So I have the point 2, 6, and if I graph those two equations, I can see indeed they are two lines that intersect in the plane, and they intersect at the point 2, 6. So there's our first systems of equations lesson using the method of substitution to solve the systems. Come to class next time and we'll practice the substitution method.